Welcome to Mississippi State University, and welcome to the Department of Building Construction Science. This is BCS 8123, Research Methodology in Construction. I'm glad you're here, and my hope is that this class really helps you grow your research skills. This course is designed for graduate students in construction programs, and the goal is pretty simple: help you build a research toolkit you can actually use in your career. Over the semester, we'll practice things like defining a clear problem, developing good hypotheses, collecting appropriate data, analyzing it, and then presenting your findings in a way that supports better decisions in construction. This class also gives you a foundation for the rest of your construction management courses at MSU, whether you plan to follow a research track or not. We're not going to treat research as something scary or overly academic. We'll treat it more like a project or a voyage of discovery. If you've worked on construction projects before, you already know the pattern. There's a clear beginning, a middle where most of the work happens, and an end where you deliver a high-quality outcome. Research follows that same kind of life cycle. Throughout the semester, we'll try to move beyond just fixing surface-level problems. In construction, it's common to patch the crack. In this course, you'll learn how to diagnose the foundation instead. We'll focus on understanding why problems happen, so that we can develop systematic, evidence-based recommendations. To do that, we'll start by identifying the gap between what is and what should be, then look at what others have already done so we're not reinventing the wheel, and finally choose an appropriate research design to study the problem. You'll also get an introduction to some big ideas behind research. We'll talk about the positivist view, which looks for objective, general patterns using logic and data, and the interpretivist view, which focuses on how people understand and react to events. You'll see how quantitative methods can show overall trends, while qualitative methods can reveal deeper motivations and experiences. We'll also look at triangulation, using both numbers and stories together to build stronger conclusions. On the practical side, we'll cover topics like sampling design. You'll hear about what we'll call the rule of representation. If you want to understand your whole target group, your sample needs to include a bit of every layer in that group. By the end of this course, whether you're aiming for leadership roles in industry or considering more advanced academic work, you should have a research toolkit that is systematic, logical, data-driven, and repeatable. So welcome to the start of your journey into the empirical side of construction. Construction is a project-oriented field. It covers a lot: property development, building design, construction operations, and facilities management. Because you already think in projects, you're actually in a good position to understand the research process. In project management, a project has a clear start, a middle where the work is carried out, and an end where you deliver a defined result. That life cycle is very similar to how a research study works. In our context, research is more than just looking something up. It's a disciplined inquiry that aims to contribute to a formal body of knowledge or theory. You can think of it as a kind of voyage of discovery, where the way you investigate is just as important as the technical results you produce. A lot of people in the industry are very good at day-to-day problem solving, but research is different. Instead of just patching a crack, research asks, why did the crack appear in the first place? What's really going on underneath? The goal is to understand the root causes so we can make broader, systematic recommendations for the industry, not just quick fixes on one project. For that to work, good research in construction has to rest on 5 key characteristics. It needs to be systematic, meaning it follows a planned sequence. It has to be logical, built on clear reasoning. It must be empirical, grounded in real data and observable evidence. It should be reductive in the sense that we take specific findings and show how they generalize. And it has to be replicable, so that other researchers can repeat what you did and get similar results. If you bring the same level of discipline and structure to your research that you bring to a well-run project, you end up with a solid blueprint for advancing construction knowledge.
So what exactly do we mean by research? Formally, research is a systematic investigation aimed at increasing the sum of human knowledge. Again, you'll hear it described as a voyage of discovery. And in that metaphor, the journey, the evidence you gather, and the way you reason about it are just as important as the final answers. For something to count as academic research, it has to be a disciplined inquiry. That means it's intentionally designed and structured with the specific purpose of contributing to a body of knowledge or theory. That's very different from casual curiosity, like Googling an answer to a question. In academic work, being critical and even a bit skeptical is essential. You're expected to support your assertions with evidence and to use systematic study to establish facts and reach new conclusions. If you think about it this way, research really is a learning process, arguably the deepest kind of learning, because you're not just absorbing knowledge, you're helping create it. It's important to distinguish between research and everyday problem solving because they serve different purposes. Problem solving is about fixing an immediate issue. It's like treating a symptom. Something is broken, so you fix it so work can continue. Research is more about understanding what's causing that issue in the first place. Instead of just solving the immediate problem, you're asking, why is this happening? So you can make recommendations that have a longer-term impact. In construction, the same logic applies. Instead of just tightening a safety rule when accidents happen, research asks what's really driving those incidents. Supervision, culture, training, workload, or something else. So research diagnoses the foundation, not just the visible crack. In the slides, formal research is described as having 5 key characteristics. First, it's systematic. You're not just wandering around collecting observations. You follow a planned, rigorous sequence of steps. Second, it's logical. Your study should hang together structurally. Your conclusions should follow from your data and your reasoning, not from assumptions you haven't tested. Third, it's empirical. That means it's rooted in reality, based on data, measurements, and observable evidence, not just opinion or intuition. Fourth, it's reductive. Here, reductive means that you can take detailed, specific findings and generalize them to a broader context or similar populations. Finally, it's replicable. Someone else should be able to follow your recipe, your methods, your instruments, your analysis, and arrive at similar results. That's part of what separates a scientific study from a one-off report or an anecdote.
Every study starts with a research problem, and getting this right is critical. A research problem shows up when there's a clear gap between what is happening and what should be happening. That gap is what you want to understand. In construction, many of these problems come straight from your own experience, your projects, internships, or workplaces. You might see performance issues, inconsistent safety practices, low technology adoption, or repeated cost overruns. Any of these could be the starting point for a research problem. But not every annoyance on a job site is a research problem. To qualify, the problem has to be researchable, and it has to matter. If nothing meaningful happens when it's left unsolved, it may not be worth a formal study. Once you identify a potential problem, you need to define it carefully. That means asking who is affected, how big is the problem, how often does it occur, in what social, cultural, or organizational context. You'll also check the literature. What do we already know about this issue, and where are the gaps? You should also ask, what happens if this problem remains unsolved? That helps you explain why the topic is important. If your problem statement is fuzzy or poorly framed, your methodology will be shaky. If it's clear and well justified, it becomes a solid anchor for the rest of your study.
You can think of the research process as a kind of scaffold, one step building on another. It starts with identifying a specific problem or phenomenon you want to investigate. Once you have that, the next move is to review the existing literature so you know what has already been done and where the gap is. That's how you avoid reinventing the wheel. From there, you formulate a clear research question or a set of hypotheses. With that in place, you choose a research design. You pick a paradigm, for example, positivist or interpretivist, decide on your sampling strategy, and select the methods you'll use. After the design is set, you go into the field to collect data through surveys, interviews, observations, or other methods. Then you analyze that data, interpret what it means, and finally publish or present your findings so they can feed back into the body of knowledge for others to build on. Research can be placed on a spectrum from pure to applied. Pure research, sometimes called blue sky research, is mostly about discovering fundamental theories and laws. It's driven by questions like, is this true? Or how does this work in principle? Applied research is more focused on practical use. It asks, does this work in the real world? Or how can we solve this specific problem? In construction management, you usually sit somewhere in the middle. You might be using established theories from psychology, management, or engineering to address very practical questions about safety, productivity, or technology adoption, while at the same time contributing back to theory. So your projects often use scientific knowledge to solve real problems, and if designed well, they also help refine or extend that knowledge. This slide uses 2 metaphors here: quantitative research as the grid and qualitative research as the flow. Quantitative research is about numbers and statistics. It looks for general patterns and measures how much one variable is related to another. Questions often sound like how much, how many, or to what extent. Qualitative research is about words, meanings, and experiences. It digs into how people think, feel, and interpret events. It's not a soft option, it's demanding because you're studying phenomena in their natural settings and dealing with complex, messy human behavior. In construction research, a powerful strategy is triangulation, using both approaches together. The numbers show you the pattern, the narratives help you understand why that pattern exists. When both line up, your conclusions are much stronger. A paradigm is your basic worldview about what reality is like and how we can know about it. Positivism lines up closely with the traditional scientific method. It assumes that reality is objective and exists independently of us. The positivist aim is to discover general laws and test existing theories using hypotheses and empirical data. This approach tries to achieve what Thomas Nagel called a view from nowhere. The researcher stays as detached as possible to avoid bias and to measure things objectively. Because it moves from theory down to data, positivism is strongly associated with quantitative methods and deductive reasoning. It's about critically investigating and testing ideas to reach verifiable conclusions.
Interpretivism starts from a different assumption, that reality is subjective, multiple, and socially constructed. An interpretivist researcher recognizes that their own perspective is part of the study. The key idea is that people act based on how they interpret their world, not just on the objective conditions around them. Because of that, interpretivist work usually doesn't begin with a rigid hypothesis. Instead, the researcher lets insights and sometimes new theories emerge from rich, detailed data, interviews, observations, documents. This bottom-up approach is very useful when you're exploring new or complex social phenomena in construction, such as culture, identity, or informal practices on site. It helps you understand the context and meaning behind what people do, not just the statistics.
Deductive reasoning is a top-down way of thinking. You start with an existing theory or general rule. From that, you derive a specific, testable hypothesis. Then you collect data to see whether the hypothesis is supported or not. This approach fits very well with positivism and quantitative research. It's especially suitable in areas where there is already a mature body of knowledge, and you want to see if those general rules apply in a particular context. Because deduction follows a planned, logical sequence, it helps ensure your work is systematic and replicable. You're using data to test the theory, to see if it holds in your setting. Inductive reasoning moves in the opposite direction. You start with specific observations, cases, interviews, examples, and look for patterns in what you're seeing. From those patterns, you build tentative hypotheses, and eventually a more general conclusion or a new theory. Induction is especially useful in newer areas of research where not much is known yet, and your main goal is to explore and understand what's going on. In construction research, if you're working in a nascent area, say a new technology or a new kind of work arrangement, inductive reasoning lets the data lead you. You discover patterns first, and then you build the theory. Exploratory research comes into play when the problem is not well defined, or when there's very little prior information. You can think of it as a scouting mission. The goal is to clarify the problem and get enough understanding to ask better, more precise questions later. Exploratory work often relies on qualitative methods, interviews, focus groups, observations, to surface hidden patterns and motivations. In construction, exploratory studies are useful when you're dealing with emerging topics, like new technologies, novel contract forms, or mental health issues that haven't been studied deeply yet. This work provides the initial framework for later descriptive or explanatory studies. Descriptive research is the next step when you already have some idea of the problem and want to describe it more systematically. The aim is to document the state of play, who is affected, what is happening, where it occurs, and when it occurs. In construction, this might look like a survey of safety practices across different company sizes, or a mapping of project manager demographics across sectors. Descriptive research doesn't necessarily explain why things happen, but it creates a solid, objective record that later studies can build on. Explanatory, or causal research goes a step further. It's not just describing patterns, it's trying to understand cause and effect. Here, you're asking questions like, does this management style cause more delays? Does this type of contract lead to more change orders? To answer those questions, you often need stronger designs, experiments, quasi-experiments, or advanced statistical modeling to isolate variables and measure their impact. In construction, explanatory research helps you build a causality chain. That's what allows you to make stronger recommendations, like if we change this practice, we can reasonably expect this outcome.
In any empirical study, you start by defining your population. That's everyone or everything you're interested in. For example, all construction managers in a particular region. Most of the time, you can't collect data from everyone, so you select a sample, which is a smaller group drawn from that population. The slides use the cake analogy. The population is the entire cake, your sample is a slice. For your results to be meaningful, that slice needs to contain a bit of every layer. That's the rule of representation. If your sample is biased, if it misses some layers, your conclusions won't reflect the full population. The slides also distinguish between probability and non-probability sampling. In probability sampling, everyone in the population has a known chance of being selected, methods like simple random sampling or systematic sampling. These approaches give you stronger generalizability. Non-probability sampling is used when the population isn't fully known or is hard to reach, or when resources are limited. Methods like convenience and purposive sampling fall into this category. They're useful and sometimes necessary, but you have to be transparent about their limitations.
Finally, let's talk about 3 common research styles. Surveys are great for collecting data from larger samples using structured questionnaires. They give you a snapshot of attitudes, behaviors, or conditions at a point in time. Case studies go in the opposite direction. They look deeply at a single case, a project, a firm, or a specific event in its real context. They're very useful when you want to understand why something happened in detail. Experiments and quasi-experiments focus on cause and effect by manipulating one variable while trying to control others. True lab-style experiments are rare in construction, but you can still design field or quasi-experimental studies. For example, testing how different safety messages or visual designs influence behavior. Choosing the right style depends on your research question. Picking the right tool helps you build a research design with solid structural integrity. This concludes our discussion on Introduction to Research Methodology in Construction.